Alright, so in this video we're going to do the integral formula for the inverse cotangent of x, so that's arccotangent of x. And there's two ways to approach this one. So just like with the inverse cosine integral, there's two ways to approach. One of them is to do it using integration by parts, and the other way is to do it by using inverse trig identities. So now when we did the inverse tangent integral, remember we did integration by parts and we said let u be the inverse tangent of x, so then du, so u was the inverse tangent of x. So if you watch that video you'll remember this maybe. U is the inverse tangent of x, so du is 1 over x squared plus 1 dx. Well, we could do this one exactly the same way. Okay, we'd have u be the inverse cotangent of x, okay? And the inverse cotangent of x derivative is the exact same thing, but with the minus sign in front of it. So it would really work out to be almost exactly the same. I mean, the math would be almost identical. The only difference would just be a minus sign here would change a few things along the way, but nothing really major. But so since it is pretty similar, let's not do it that way. Let's use inverse trig identities, really just one identity, like we did with the inverse cosine integral. So what we're going to do is use this identity that says arctan of x plus arccotangent of x equals pi over 2. Okay. So it's a very similar identity to the one, remember arcsine of x plus arccosine of x is pi over 2. Well, similarly, arctan of x, this is arctan of x, plus arccotangent of x equals pi over 2. Provided that x is in the domain of both of these guys, but we don't really want to worry too much about domains here. We're not really getting too deep into it. We don't want to worry about anything crazy happening or anything. So we'll just assume that everything's okay with the domain. And it's indefinite anyway, so we don't really want to concern ourselves too much, not at this stage anyway. So let's go ahead and use this. How do we use this? Well, subtract arctangent of x from both sides, and we get, might need a different blue here, we get arccotangent of x equals pi over 2 minus arctan of x. Okay. All right. So inverse cotangent of x is the exact same thing as pi over 2 minus arctan of x, provided x is in the domain of both these guys, and so on. So if we want to integrate this, let's just go ahead and integrate, let's say this equals the integral of pi over 2 minus arctan of x dx. Okay? And then parentheses because the dx is on everything. So all right, now we can split this guy up into two integrals. So that's the integral of pi over 2 dx minus the integral of arctan of x dx. Okay. Now if we integrate pi over 2, we just get pi over 2x plus some arbitrary constant I'm going to call c1, or really we can just call it whatever. Let's just call it c. Okay. And then minus, so what is the integral of arctangent? So we did that in the previous video, and if you saw that, then maybe you'll recall that the answer to that was x arctangent of x minus 1/2 natural log of x squared plus 1 plus an arbitrary constant, which now I'm going to use c1 because I already used c over here, so I should use a different constant name over here because these might be different constants. We don't know. They're arbitrary. We don't know. Okay, so now so let's simplify everything here. So this is pi over 2 x, let's hold off on the constants till the end, so this is going to be minus x arctangent of x. Minus negative means plus 1/2 natural log of x squared plus 1. Alright, and then what do we have here? We have plus c, and then minus c1, okay? Okay, now, again, just like in the inverse cosine integral video, we have an arbitrary constant minus some other arbitrary constant. So if you subtract two arbitrary constants, you're going to get another arbitrary constant. So we could just squash these guys into one and just say plus c. So really I could have kept that c there, I guess. But anyway, so subtle details, I want to point out this c is going to be different probably from this c, right? But it doesn't really matter, okay? So as long as, since these guys were on the same line, then we had to say c and c1, okay? But here we're just going to squish them together into one constant, and we're just still going to call that constant c. Okay, why is that? Well, again, we could say c2, but there's really no point because this constant and this constant got absorbed together. So these two guys are really gone. They're squished into one constant, so we can just keep calling it c. And again, it's just an arbitrary constant. We don't know what it is. We don't care what it is, not at this point anyway. All we know is it's just some arbitrary constant, so it could be positive, it could be negative, it could be 0. We don't care yet. But to keep things as simple as possible, we just say blah, blah, blah plus c, okay? So just want to keep it all as simple as possible. Because, you know, if this were just, this is just some constant, that's some other constant, so constant minus a constant is just another constant. So arbitrary constants work nicely together like that, even if it is kind of weird. So anyway, this, you know, we could leave it here, but it's not as simplified as it can be. Also, the original problem was the integral of arccotangent, so it'd be nice if the answer would involve that somehow, if possible. And here, we could simplify this a little bit. So just like in the inverse cosine integral video, let's factor out an x here. So this is pi over 2 times x, arctangent of x times x. So let's factor out an x. What we have left is pi over 2 minus arctangent of x. Okay. And then still plus 1/2 times natural log of x squared plus 1 plus that arbitrary constant. Now, why do we factor out this x? Well, what's left in here? Pi over 2 minus arctan of x. Is that something? Yeah, pi over 2 minus arctan of x is arccotangent of x. Okay, pi over 2 minus arctan x, that is arccotangent of x. Pi over 2 minus arctan x, that is arccotangent. So this is x arccotangent of x. And then we have plus 1/2 natural log of the quantity x squared plus 1. Okay, and then plus c. Okay, so really that's it. So this is the integral of arccotangent of x dx. Okay. So this is the integral formula for the inverse cotangent function. And again, just like with the inverse tangent integral, first of all, we could have done this using integration by parts and we get the same thing. Notice, let's compare this to the other integral. So the integral of arctan of x dx is x arctan x minus 1/2 natural log of this x squared plus 1, then plus an arbitrary constant. And over here, this is the integral of this arccotangent of x dx is x arccotangent of x plus 1/2 natural log of x squared plus 1 plus c. Okay. So notice the difference in signs here, minus and then plus. So really, this is very parallel to the inverse cosine integral video, if you saw that. So it's very parallel in that we used a similar identity. We had the same kind of thing here going on with the combining the arbitrary constants into another arbitrary constant, and we had the same sort of parallel thing going on here with this integral formula and the other integral formula that we used. So just a difference in the signs and all that, and the inverse trig function that appeared. So really quite a few parallels there. And also one last thing to point out, remember the inverse tangent integral, we could express it like this, or we could say, we could bring this power up as a factor. So remember r times the natural log of m, or any base log, is the natural log of m to the r. Okay, so we could bring up the 1/2 as a power, and remember a power of 1/2 means a square root. So we could also say natural log, yikes, we could say natural log of the square root of x squared plus 1. Okay, so just remember that. Then this would be natural log of square root of x squared plus 1, same thing over here, and then this would become natural log of the square root of x squared plus 1, and so on. So let's go ahead and write that just to be thorough. So you might see this, if you're looking at a table of integrals or integral formulas, stuff like that, you might see the formula expressed like this, or you might see it expressed like this. So you'll have x arccotangent of x, dx over here, plus natural log of the square root of x squared plus 1, and then plus c. So it might be like this, or it might be like this. Okay? And again, just the reason is because powers on logs can come up as factors like that. So that's just a pre-calculus thing. So here's two different forms. They're really equal to each other, of course. Two different forms for the inverse cotangent formula, inverse cotangent integral formula. So that's the integral formula for the arccotangent of x. So we could have used integration by parts, but we went the simpler route and just used this identity here, just like with the arccosine integral. So that's that.